Welcome, dear listener. I'm Tina, scientist and lifelong terrible sleeper. I made AI for sleep to help ease my own restless nights after I learned a busy mind tends to drift off when it's gently occupied, not forced quiet. So everything here is built to give your thoughts somewhere soft to land. Let yourself settle in wherever you are, perhaps pulling a soft blanket closer or adjusting your pillow just so. Tonight we're going to explore something that might seem complex at first, but I'll be right here with you as we walk through it slowly. We're looking at why the costs of artificial intelligence are changing in ways that might surprise you, and how the shift toward AI agents is quietly reshaping the very economics of computing. There's a hidden reason your AI costs are about to shift dramatically, and we'll discover it together, one careful step at a time. Let's begin with how the economics of machine learning have traditionally worked, like a comfortable pattern we've grown used to. But first, a gentle observation. Most of the people who drift off to this channel have never actually hit subscribe. So if I've ever helped you in any way, you can return the favor with a simple and free action that will encourage me to keep going. Now, without further ado, let's fall asleep.
Imagine you're building a custom motorcycle in your garage, spending months welding the frame, tuning the engine, and perfecting every component until it purrs like a dream. The economics of machine learning have traditionally followed this same pattern, where the heavy lifting happens upfront during training, much like those long nights in the garage, and then you get to enjoy countless rides on smooth highways with minimal fuel costs during inference. But as we'll explore tonight, this comfortable assumption is shifting beneath our feet, especially as AI systems become more like thoughtful agents than simple prediction machines. Think of training a neural network like charging a massive hydroelectric dam, where you're pumping enormous volumes of water uphill using industrial-scale machinery that consumes tremendous energy for weeks or months. During this training phase, companies routinely spend hundreds of thousands or even millions of dollars on compute clusters, burning through electricity and hardware time as they process vast data sets and adjust billions of parameters. The assumption has always been that once your dam is full, once your model is trained, you can generate electricity, or in our case predictions, at a relatively modest cost per unit. Traditional inference has been like plucking ripe apples from a well-established orchard, where each individual apple costs very little to harvest once the trees are mature and the infrastructure is in place. A single forward pass through a trained model, whether it's classifying an image or translating a sentence, typically consumes orders of magnitude less compute than the training process that created it. This economic structure made perfect sense for the first generation of AI applications, where you train once and then serve millions of simple, independent queries with predictable resource requirements. But here's where things get interesting, like watching a master chess player who doesn't just glance at the board and make a quick move, but instead sits back, studies multiple potential sequences, considers various strategies, and sometimes even backtracks to reconsider earlier assumptions. Modern agentic AI systems are starting to behave more like this contemplative chess master during inference, spending significant computational resources on reasoning, planning, and iterative problem solving, rather than just producing a single, immediate response. Consider how a skilled detective approaches a complex case, not by immediately announcing a solution, but by gathering evidence, forming hypotheses, testing them against new information, consulting with experts, and sometimes completely revising their theory when contradictory facts emerge. Agentic AI systems are increasingly following this same pattern during inference, where a single user query might trigger extensive internal reasoning, multiple tool calls, self-correction loops, and iterative refinement processes that can consume substantial computational resources for each individual request. This shift is like the difference between a traditional vending machine that simply dispenses a pre-made snack when you insert coins, versus a short order cook who needs to actively prepare your meal from scratch, tasting, adjusting seasonings, and potentially starting over if something doesn't turn out right. The vending machine model worked perfectly for classical machine learning, where inference was cheap and predictable, but agentic systems often require dynamic, variable amounts of compute that can't be easily predetermined or batched efficiently.
This creates what economists call variable cost structures,
where some queries might require minimal processing while others trigger extensive reasoning chains that could consume dramatically more compute than a basic response, much like how a master watchmaker might quickly adjust a simple timepiece, but spend hours diagnosing and repairing a complex chronograph with multiple complications. Picture a library where most visitors used to simply check out books they'd already identified. But now many patrons arrive asking complex research questions that require the librarian to consult multiple sources, cross-reference information, synthesize findings, and sometimes even reach out to other libraries for additional resources. Each patron interaction becomes a mini research project with unpredictable duration and resource requirements, fundamentally changing the staffing and infrastructure needs of the library.
This unpredictability creates what we might call the computational burst problem,
Similar to how a restaurant might easily handle a steady stream of simple sandwich orders, but struggles when multiple customers simultaneously request elaborate multi-course meals that require extended preparation time and coordination between different kitchen stations. Traditional infrastructure provisioning, designed around predictable inference loads, becomes inadequate when individual requests can suddenly spike resource consumption by orders of magnitude.
The economic implications ripple outward like stones thrown into a calm pond,
affecting everything from pricing models to infrastructure design to competitive dynamics in the AI industry. Companies can no longer simply amortize training costs across millions of cheap inference calls, because those inference calls themselves might require substantial computational investment, especially for complex reasoning tasks that push the boundaries of what we expect from AI systems. Consider how this changes the fundamental unit economics. Much like the difference between manufacturing identical widgets on an assembly line versus running a custom fabrication shop, where each order requires unique tooling, materials, and expertise. The assembly line model allowed for precise cost prediction and efficient resource utilization. But custom fabrication introduces variability that makes pricing, capacity planning, and profitability much more complex to manage. From an infrastructure perspective, this shift is like transitioning from managing a steady flow pipeline that moves a consistent volume of liquid from point A to point B to orchestrating a complex irrigation system with multiple branches, variable flow rates, and dynamic routing based on real-time conditions. The pipeline model worked beautifully for traditional batch processing and simple inference workloads, but agentic systems require more sophisticated resource management and allocation strategies.
the competitive landscape transforms as well, resembling how the taxi industry operated with predictable routes and standardized pricing, until ride-sharing introduced dynamic pricing, surge multipliers, and variable service levels that completely restructured the market dynamics. Companies that built their business models around cheap, predictable inference costs now find themselves navigating a world where the most valuable AI capabilities might also be the most expensive to deliver. This creates fascinating strategic decisions, like a power company choosing between building steady output coal plants versus more expensive but flexible natural gas turbines that can quickly ramp up and down to meet variable demand.
Some companies might optimize for consistent, lower capability inference that maintains predictable costs, while others might invest in the infrastructure needed to support high variability, high capability agentic workloads despite the economic complexity.
The user experience implications are equally profound.
Similar to how streaming services had to evolve from simple video delivery to sophisticated recommendation engines, personalized interfaces, and interactive content that requires real-time processing and adaptation. Users increasingly expect AI systems to provide thoughtful, contextual, and personalized responses rather than generic outputs. But these expectations come with computational costs that must somehow be balanced against economic realities.
Looking toward the future, we're likely entering an era where inference economics become as complex and strategically important as training economics have traditionally been. Much like how a master gardener must balance the long-term investment in soil preparation and plant selection with the ongoing variable costs of watering, pruning, and pest management throughout the growing season. The simple train once, infer cheaply model is giving way to a more nuanced understanding of computational economics, where both phases require careful optimization and strategic thinking.
What we just heard was that gentle comparison between building a motorcycle and training AI models, where most of the hard work and expense traditionally happened up front during training, leaving inference to be relatively inexpensive afterward. It's a comforting model that many have relied on for years, but as you're resting with that thought, you might sense that something fundamental is shifting. Let's take a slow breath together and turn our attention to just how dramatically the demand for AI computing has grown. The next part of our journey will show us the sheer scale of what's happening in the world of artificial intelligence right now.
Picture a massive industrial factory where the production line has suddenly shifted into overdrive, with conveyor belts moving so fast they're almost a blur, and workers scrambling to keep pace with demand that seems to multiply by the hour. That's essentially what NVIDIA CEO Jensen Huang described at Dell Technologies World this week, when he told the audience that AI demand has gone utterly parabolic, transforming computational workloads that once took months into tasks completed in mere hours, creating what he calls a gigantic leap in computation requirements that's driving enterprises from experimental pilots into full-scale production deployments.
Michael Dell opened the keynote by sketching the financial landscape of this transformation,
painting numbers that would make any CFO take notice, with worldwide AI infrastructure spending projected to reach $3 to $4 trillion by 2030, while token consumption, the fundamental unit of AI processing, is expected to grow by a staggering 3,400% in that same timeframe. Think of this like watching a small mountain stream during spring snowmelt, where what starts as a gentle trickle becomes a rushing torrent that carves new channels through the landscape, fundamentally reshaping everything in its path. And that's exactly what's happening as enterprises move beyond tentative AI experiments into what Huang calls the era of truly useful artificial intelligence.
At the heart of this computational revolution
sits the new NVIDIA Vera Rubin NVL72 architecture, integrated into Dell's PowerEdge XE9812 servers, which delivers agentic AI inference at 1/10 the cost per token compared to previous generation systems. Imagine a master locksmith who has perfected their craft to the point where they can open complex locks in seconds rather than minutes, using precisely the right amount of force and exactly the right technique. And that's how Vera Rubin approaches AI inference, applying computational power with such efficiency that enterprises can now afford to run sophisticated AI agents continuously, rather than rationing their use due to cost constraints. The NVIDIA Vera CPU represents a different kind of breakthrough, engineered specifically for the sequential, interdependent nature of agentic AI workloads, where each step must wait for the previous one to complete. Picture a master chef's knife, perfectly balanced and razor-sharp, designed for the precise, rapid chopping that transforms raw ingredients into a finished dish. And that's how Vera CPU handles the data pipelines, analytics, and sandboxed code execution that modern AI agents require, delivering 1.2 terabytes per second of memory bandwidth and completing these sequential workloads 50% faster than traditional x86 processors. Wang emphasized that Vera CPU achieves the highest single-threaded performance of any CPU in the world, with 3 times the memory bandwidth of conventional processors, making it particularly effective for database operations that AI agents constantly access. Consider a librarian who has memorized not just where every book is located, but can instantly recall the contents of any page, moving through the stacks with supernatural speed and precision to gather exactly the information needed. And that's how Vera CPU handles the intense database queries that modern AI agents generate, with systems like Starburst and DuckDB running dramatically faster because the agents are, as Wang put it, pounding on the databases with continuous requests. Dell's AI data platform has been redesigned around accelerated data engines built on NVIDIA's CUDA-X libraries, including QDF for structured data and QVS for unstructured data, with the Starburst data engine delivering 3 times faster query throughput on Vera CPU for large-scale SQL analytics. Think of this like a sophisticated water treatment plant where multiple specialized filters and processors work in parallel, each optimized for different types of contaminants, transforming raw input into precisely the clean, usable output needed downstream. And that's how these accelerated data engines process the vast streams of enterprise information that feed modern AI systems, ensuring that agents have immediate access to clean, structured data regardless of its original format. The enterprise adoption stories shared during the keynote reveal how this technology translates into real-world impact, with companies like Eli Lilly using Dell AI factory infrastructure to advance life sciences research at unprecedented scale. Diogo Rao, Lilly's chief information and digital officer, described their work with the optimism of a gardener who has discovered a new growing technique that could revolutionize agriculture, explaining how AI-driven advancements in drug discovery and development are bringing them closer to what was unimaginable 20 years ago, the possibility of ending disease as we know it, powered by AI infrastructure that can process biological data and molecular interactions at scales previously impossible. Samsung showcased their use of the Dell AI Factory for research and development in chip design and manufacturing, while Honeywell's Chief Technology Officer, Suresh Venkatarayalu, explained their strategic shift from public cloud to on-premises AI infrastructure for industrial applications, digital twins, and automation spanning from data center to edge deployments. Picture a master architect who decides to move their design studio from a shared co-working space into a custom-built facility where they control every aspect of the environment, from lighting to acoustics to security. And that's how these enterprises are approaching AI infrastructure, recognizing that the most sensitive and valuable AI workloads require the control and security that only on-premises deployment can provide. Dell's own research reveals this shift toward on-premises AI deployment, with their survey finding that 67% of AI workloads now run outside the cloud, distributed across on-premises data centers, edge devices, and co-location facilities, while 88% of respondents operate at least one AI workload on their own infrastructure. This trend resembles a master baker who starts by purchasing bread from various suppliers, but gradually builds their own bakery as they realize they need complete control over ingredients, timing, and quality to create exactly what their customers demand. And enterprises are making similar decisions about AI, bringing critical workloads in-house where they can ensure security, governance, and performance meet their exact specifications. Security concerns drive much of this on-premises adoption, addressed through NVIDIA confidential computing technology, delivered in partnership with companies like Fortanix, Google, and Red Hat, creating secure environments where enterprises can deploy frontier AI models without exposing sensitive model intellectual property or confidential data. Think of this like a diplomatic pouch
that allows sensitive documents to travel through potentially hostile territory while remaining completely secure and unreadable to anyone who might intercept them. And that's how confidential computing protects AI models and enterprise data even while they're actively being processed, ensuring that companies can leverage the most advanced AI capabilities without compromising their competitive advantages or regulatory compliance.
Google Distributed Cloud with Gemini 3.0 is now available in preview on Dell PowerEdge XE9780 servers, accelerated by NVIDIA Blackwell and secured by confidential computing. While SpaceX AI plans to bring their latest models on-premises to Dell AI Factory infrastructure with end-to-end protection for model weights and enterprise data. This represents a new model of AI deployment, like a traveling museum exhibition, where priceless artifacts can be displayed in local venues while maintaining museum-quality security and climate control, allowing enterprises to host the world's most advanced AI models within their own infrastructure, while ensuring that both the models and their data remain completely protected throughout the entire computational process. For enterprises preferring open-source alternatives, NVIDIA Nematron models provide frontier-class open intelligence that runs natively on Dell AI Factory infrastructure, joined by Reflection's open-source models designed specifically for regulated industries, governments, and sovereign entities. Picture a master craftsman's workshop where all the tools and techniques are openly shared and can be modified for specific projects, yet the workspace itself remains private and secure. And that's how these open frontier models operate, providing transparency and customization capabilities while running within the protected confines of enterprise infrastructure, giving organizations the flexibility to tune models to their specific domains and data without sacrificing security or control. The software ecosystem extends beyond models to include comprehensive agent orchestration capabilities, with NVIDIA NemoClaw serving as the connective tissue between local models and enterprise data, while NVIDIA OpenShell provides an open-source runtime for developing and deploying autonomous agents with built-in security and privacy controls. Consider this like a sophisticated telephone switchboard operated by an expert who knows exactly how to route calls between different departments, ensuring that each connection is secure and that information flows efficiently to where it's needed. And that's how these orchestration tools manage the complex interactions between AI agents, enterprise systems, and data sources, maintaining security policies and governance requirements while enabling the fluid collaboration that makes agentic AI truly useful. Dell's partnership announcements span from Palantir's sovereign AI operating system reference architecture to ServiceNow's enterprise workflow automation, along with collaborations with companies like FogSphere, Ipsotech, Mistral AI, Poolside, and Unique, plus security partnerships with CrowdStrike and Fortanix. This ecosystem development resembles a master shipbuilder who doesn't just construct the hull, but carefully selects and integrates specialized components from the finest suppliers, each contributing their expertise to create a vessel that's greater than the sum of its parts. And that's how Dell is approaching the AI infrastructure market, recognizing that enterprises need not just powerful hardware, but complete solutions that integrate seamlessly with their existing tools, workflows, and security requirements. The announcement of Dell Desk-Side Agentic AI brings this enterprise-grade AI capability down to individual workstations, running on Dell Pro Max systems with NVIDIA GB10 and GB300 processors powered by the Grace Blackwell architecture, as well as Dell Pro Precision systems with NVIDIA RTX Pro Blackwell workstation platforms. Think of this like a master jeweler's personal workbench, equipped with all the precision tools and magnification equipment needed for the most delicate work, but scaled down to fit in their private studio rather than requiring access to a massive factory floor. And that's how desk-side agentic AI transforms individual productivity, giving knowledge workers access to sophisticated AI agents that can understand their specific context, integrate with their personal workflows,
and operate with the same security and governance standards as enterprise-scale deployments.
We've just seen those striking numbers that Michael Dell and Jensen Huang shared about the explosive growth in AI demand, with infrastructure spending reaching trillions and token consumption growing by thousands of percent. Those are big numbers, and it's perfectly natural if they feel overwhelming. You don't need to hold on to every detail. Just let the sense of massive change settle gently in your mind. As we continue our quiet exploration, we're going to discover how this surge in demand is leading to something entirely new, something called AI factories. Let these new ideas come to you slowly, like morning light gradually filling a room.
Imagine a bustling textile mill from the industrial age, with its spinning wheels turning raw cotton into finished cloth around the clock. This is the closest analogy we have for understanding what AI factories represent in our current technological moment. These facilities represent a fundamental shift in how we think about artificial intelligence infrastructure, moving beyond simple software applications to become continuous manufacturing systems for intelligence itself. Just as those historical mills converted raw materials into valuable products through coordinated mechanical processes, AI factories convert electrical energy into tokens, which serve as the fundamental unit of production for reasoning models, autonomous agents, and intelligent systems that operate without human intervention.
The economics of these AI factories flow like water through a carefully engineered dam system,
where every aspect of the infrastructure must be optimized to maintain steady output and prevent bottlenecks. Performance metrics center on tokens per second, tokens per watt, cost per token, utilization rates, and uptime percentages, creating a direct relationship between energy efficiency and revenue generation. Unlike traditional data centers that primarily stored and retrieved files, these facilities actively manufacture intelligence as their core product, making performance per watt the ultimate measure of competitiveness in this new landscape.
think of a master conductor orchestrating a symphony with hundreds of musicians, each playing their part in perfect synchronization to create something greater than the sum of individual performances. AI factories coordinate massive compute resources while simultaneously serving billions of requests from users around the world, requiring software orchestration that manages autonomous, multi-agent systems running continuously. These agentic systems engage in reasoning and planning using the best-performing AI models, both proprietary and open-source options like NVIDIA Nematron, with open models offering the flexibility to be customized for specific enterprise domains, optimized for particular use cases, and securely deployed within the factory infrastructure. The workload characteristics of these systems resemble a busy emergency room where multiple medical teams handle complex, interconnected cases that require different specialists and equipment throughout the treatment process. Autonomous agents don't simply respond to prompts like traditional AI systems, but engage in reasoning, planning, searching, tool usage, data retrieval, code writing, and direct action taking within their environments. These agents create their own specialized subagents that learn to use domain-specific tools and develop unique AI skills, resulting in multi-agent workflows that are longer, deeper, and far more compute-intensive than previous generations of AI workloads. Picture a high-performance race car where every component, from the engine to the aerodynamics, must work in perfect harmony to achieve maximum speed and efficiency on the track. AI factories require accelerated compute paired with fast memory, storage systems for maintaining context, networking infrastructure for coordination between agents, software layers for orchestration, and CPUs for execution tasks, with workloads moving across this entire stack while maintaining tight latency requirements at every step. The infrastructure must keep these complex workflows moving continuously with the precise balance of throughput, responsiveness, and utilization needed to produce tokens efficiently at massive scale. Consider a master chef's kitchen during peak service,
where timing, coordination, and resource management determine whether hundreds of complex dishes can be prepared and served without delay or compromise in quality. As AI workflows become longer and more interactive, the factory infrastructure must operate in real time, routing requests appropriately, managing memory allocation, coordinating services across the stack, balancing latency against throughput requirements, and maintaining high utilization across all system components. The software orchestration layer becomes critical because the factory's ability to run efficiently directly determines how much intelligence it can produce and ultimately how much economic value it creates for its operators.
Building an AI factory resembles constructing a precision Swiss watch,
where every gear, spring, and mechanism must be designed together from the beginning to achieve the desired accuracy and reliability. The same full-stack co-design principles required for efficient inference also fundamentally change how AI factories are planned, validated, and brought online, with hardware, networking, memory, storage, and software architected together through continuous optimization at every layer. This integrated approach increases utilization rates, lowers cost per token production, and raises overall output, while balancing the responsiveness needed for always-on, interactive AI workloads with the raw throughput required to maximize intelligence production.
The performance improvements delivered by next-generation hardware can be visualized like a powerful hydroelectric turbine that generates dramatically more electricity from the same volume of flowing water. NVIDIA GB300 NVL72 systems generate 50 times more tokens per megawatt compared to the previous generation, resulting in 35 times lower cost per token when compared with the NVIDIA Hopper platform architecture. These efficiency gains mean that AI factories built with NVIDIA Blackwell Ultra architecture can deliver up to 50 times higher throughput per megawatt while achieving 35 times lower cost per token, effectively balancing performance, responsiveness, and energy efficiency at unprecedented scale. The NVIDIA Dynamo framework operates like a sophisticated air traffic control system, managing the complex choreography of long context reasoning tasks and massive inference throughput, while maintaining high utilization as workloads become increasingly interactive and complex. This orchestration capability demonstrates how AI factory performance is now measured primarily by how efficiently
A facility can produce intelligence in real time, rather than traditional metrics focused on raw computational power or storage capacity. The framework ensures that the various components of the AI factory work together seamlessly to maintain continuous intelligence production without bottlenecks or inefficiencies.
Looking ahead, the NVIDIA Vera Rubin platform represents the next evolutionary step, functioning like an advanced solar panel array that captures and converts energy with dramatically improved efficiency compared to previous generations. As reasoning capabilities in agentic AI continue to scale in complexity and scope, Vera Rubin-based systems are specifically designed to push performance per watt up to 35 times higher with LPX architecture and drive token costs lower through deeper full-stack optimization across all system layers. The ultimate result is more efficient intelligence production at the factory level, enabling organizations to generate more value from the same infrastructure investments. The evolution from individual GPUs to complete AI factories resembles the transformation of a single craftsman's workshop into a fully integrated manufacturing complex with supply chains, quality control, and distribution networks. What began with graphics processing units has expanded into comprehensive AI factories comprising accelerated compute systems, high-speed interconnects, liquid-cooled infrastructure, inference software platforms, autonomous agent frameworks, reference architectures, and the complete ecosystem needed to build and operate these facilities at scale. This ecosystem includes global system partners such as Cisco, Dell, HPE, Lenovo, and Supermicro, along with curated AI software partners
who develop solutions for specific enterprise use cases across both proprietary and open model options. These AI factories can be deployed across use cases like a versatile construction crane that can build everything from small residential projects to massive skyscrapers, adapting its configuration to match the specific requirements of each job. Applications range from agentic AI workloads to physical AI implementations and robotic systems, with every organization across every industry, from financial services and life sciences to manufacturing and public sector organizations, eventually needing to either build or rent access to an AI factory. NVIDIA operates its own enterprise AI factory, with hundreds of autonomous AI agents assisting engineering, software, and operations teams, serving as a practical proof point that these facilities can transform how companies build, design, and operate their core business processes.
The scalability of AI factory implementations works like a modular greenhouse system that can start with a single growing chamber and expand into vast agricultural complexes as demand increases. Organizations can begin with small deployments supporting one business unit or specific workload, then scale up to support high-performance AI inference and training at massive scales as their needs evolve. NVIDIA DSX reference designs unify design, simulation, operations, and ecosystem technologies to enable the construction of gigawatt-scale AI factories optimized for the lowest token cost per megawatt, providing a clear pathway for organizations to grow their intelligence production capabilities over time. Building gigawatt-scale AI factories requires the same comprehensive planning approach as constructing a modern city, where architects must model transportation, utilities, housing, and commercial districts together before breaking ground on any individual building. These massive facilities need shared digital environments, where facility design, hardware systems, power distribution, cooling infrastructure, and operations can be modeled together before construction begins and continuously improved after deployment. The NVIDIA Omniverse DSX blueprint supports this workflow through digital twins that connect facilities, hardware, and software using Omniverse, OpenUSD, and SIM-ready assets, helping partners validate designs and optimize operations across the complete AI factory lifecycle. The full-stack approach to AI factories transforms organizations like a comprehensive renovation that converts a traditional office building into a smart, responsive environment where every system works together to enhance productivity and efficiency. This methodology helps organizations extract more intelligence from every system component, turning AI infrastructure into an autonomous, always-on engine of reasoning, action, and insight that integrates seamlessly into daily operations. Just as the last industrial revolution converted raw energy into mechanical work that powered economic growth, this new era converts energy directly into intelligence, with AI factories serving as the essential infrastructure foundation for the next wave of technological and economic transformation.
We've just learned about AI factories and how they represent a fundamental shift from simple software to continuous manufacturing systems for intelligence itself, converting electrical energy into tokens around the clock. Take a moment to let that image rest in your thoughts. These aren't just bigger computers, but entirely new ways of thinking about how intelligence can be produced. Now, as we move deeper into our evening together, we'll explore how the hardware that powers these factories is being designed to handle these new demands. The next segment will show us some remarkable advances in how these systems are built and connected.
Imagine a master chef organizing their kitchen for the dinner rush, where every ingredient must be perfectly positioned for maximum efficiency. As AI models grow to trillion parameters, the performance of modern computing infrastructure depends not just on raw hardware power, but on how intelligently workloads are placed across that hardware. The NVIDIA GB200 NVL72 system delivers exascale computing power in a single rack, with 72 Blackwell GPUs interconnected through the largest production-scale compute fabric ever built, providing 130 terabytes per second of low-latency communication bandwidth. Picture a bustling highway system where the fastest routes connect major cities through dedicated express lanes. The GB200 NVL72 achieves its remarkable performance through NVIDIA NVLink, which creates these express pathways between GPUs, allowing data to flow at unprecedented speeds. Recent benchmarks show dramatic improvements across all AI workloads, with training performance increasing by more than 2.6 times in MLPerf results, and inference capabilities reaching over 1.5 million tokens per second for large language models like GPT. Consider a librarian who understands exactly which books belong on which shelves, ensuring readers can find related materials clustered together efficiently. Topology-aware job scheduling works similarly, allowing resource managers like Slurm to make intelligent allocation decisions based on the physical network layout of the cluster. The scheduler preserves locality by keeping workloads within the same NVLink domain whenever possible, while also providing efficient bin packing to prevent resource fragmentation across multiple training or inference jobs.
Think of a gardener who realizes their old pruning techniques no longer work for a new variety of rapidly growing trees.
Traditional Slurm scheduling used a best effort approach that often fragmented jobs across different network switches to reduce queue times, which worked adequately for older InfiniBand fabrics but proved inadequate for rack-scale systems. In response, NVIDIA and SkedMD collaborated to develop the new topology block plugin in Slurm 23.11, specifically designed to handle the unique characteristics of modern architectures like GB200 and GB300 systems.
Envision a city planner who must balance large office complexes with smaller residential units, ensuring efficient use of every block while maintaining neighborhood coherence. The GB200 NVL72 system introduces the concept of job segment sizes, which define subunits of nodes that can communicate entirely over NVLink connections. While previous systems like the HGX H100 were limited to segment sizes of just one node, the GB200 NVL72 supports much larger segments of up to 18 nodes, while still efficiently handling single-node segments for smaller workloads. Picture a tailor who must choose the right fabric weight for different types of garments, knowing that evening gowns require different materials than casual shirts. The optimal segment size for any given application depends on factors such as model type and the combination of parallelism approaches used during training. Generally, larger jobs utilizing more GPUs and those with high bandwidth requirements like mixture of experts training benefit from larger segment sizes, while smaller jobs with lower bandwidth needs should use smaller segments to avoid over-constraining the cluster scheduler. Think of a theater manager who discovers that 90% of their revenue comes from large productions, leaving just enough flexibility for smaller shows to fill the remaining slots. Through modeling and simulation, the development team found that choosing a critical job size using 16-node segments, such that those jobs consume no more than 90% of the cluster's GPU hours, provides optimal flexibility for the scheduler. This approach allows for a healthy mix of segment sizes while maintaining high overall utilization. Consider a puzzle master who has developed a systematic approach for fitting pieces of different sizes together, ensuring no space goes unused. The recommended configurations follow clear patterns, with 128 GPU jobs using 16-node segments for mixture of experts training, 32 to 64 GPU jobs using 4-node segments for large dense model training, and jobs smaller than 32 GPUs using single-node segments. These power of 2 segment sizes enable efficient scheduling where large 512 GPU jobs can run alongside several smaller 16 GPU jobs simultaneously. Imagine a flight simulator
that allows pilots to practice emergency procedures without risking actual aircraft, providing realistic scenarios in a controlled environment. NVIDIA and SkedMD developed a standalone Slurm simulator that runs on virtual machines and enables time-accelerated workload simulation. This simulator accurately replicates real-world conditions by running actual Slurm code, replaying production workloads, or generating synthetic ones, simulating node failures and recoveries, and integrating with metric systems for direct comparison of results. Picture a stress testing laboratory where engineers subject materials to extreme conditions to understand their breaking points and optimal performance ranges. The simulation environment modeled a substantial cluster with 5,000 GB200 NVL72 nodes, totaling 20,000 GPUs, running 15,000 jobs over a 7-day period, with an average of 2.5% of nodes experiencing downtime at any given moment. The team evaluated performance using a large perf custom policy designed to balance utilization and large job performance, where jobs with 32 nodes or more used 16 node segments, while smaller jobs used 2 node segments. Think of a skilled apartment building manager who strategically places small tenants in corner units, preserving the larger, more desirable spaces for families who need them most. The simulation results revealed that the topology plugin effectively placed small jobs on the last 2 nodes of each NVLink domain, minimizing fragmentation and preserving capacity for larger jobs that require extensive interconnected resources. This intelligent placement strategy ensures that high bandwidth workloads can access the full performance benefits of the NVLink fabric. Consider a tightrope walker who maintains perfect balance while moving forward, demonstrating that constraints can coexist with optimal performance when properly managed. The occupancy metrics showed that topology-aware scheduling achieved utilization within roughly 1% of the theoretical maximum possible with topology-naive scheduling, proving that intelligent placement doesn't require sacrificing overall cluster efficiency. This near-optimal occupancy was achieved while avoiding the significant performance penalties that would result from poor job placement across network boundaries. Picture a Maston navigator who charts courses not just for today's voyage, but continuously updates their maps based on changing weather patterns, seasonal variations, and emerging navigation technologies. For GB200 NVL72 clusters, continuous monitoring and adjustment of topology-aware scheduling becomes essential, tracking fragmentation metrics as workload patterns evolve, and validating policy changes through simulation before production deployment to ensure optimal resource utilization. Envision a precision instrument maker who has crafted a complex device where every component contributes to exceptional accuracy and reliability, each element designed to work in harmony with all others. The GB200 NVL72 system represents this level of engineering sophistication in AI computing, where unlocking exascale performance requires the careful orchestration of topology-aware scheduling, segment-based job placement, and continuous optimization to achieve both maximum throughput and efficient resource utilization across the entire computational fabric.
I'm curious how this one sits with you. Does the idea of where all of this is heading comfort you or quietly unsettle you? Tell me in the comments. I read them on my own sleepless nights. We've just seen how modern AI systems require incredibly sophisticated hardware, like that NVIDIA GB200 system, with its 72 interconnected GPUs and express pathways for data to flow at unprecedented speeds. Those technical details might feel dense, but the essential idea is simple. The hardware itself is evolving to meet new challenges. Rest easy knowing you don't need to remember every specification. What matters is understanding that as AI changes, so must the infrastructure that supports it. In our next gentle exploration, we'll discover how AI agents work differently from traditional AI, creating new kinds of uncertainty in how much computing power they'll need.
Picture a detective who used to solve cases by consulting a single database, but now orchestrates multiple specialists, evidence analysts, and field investigators who work together in complex, iterative workflows. Traditional AI inference followed predictable patterns where you could estimate costs based on input size and model complexity. But agentic AI introduces fundamental uncertainty because each query might spawn autonomous reasoning processes, tool usage, and multi-step problem solving that varies dramatically in computational requirements. Consider a master chef who has evolved from preparing individual dishes to orchestrating entire multi-course experiences where each course influences the next, requiring constant tasting, adjustment, and sometimes completely changing direction mid-meal based on how flavors develop. Modern AI agents don't just process inputs and return outputs, but engage in reasoning loops, self-correction, tool invocation, and iterative refinement that makes resource planning fundamentally more complex than traditional batch processing scenarios. The economics of agentic inference resemble a research laboratory, where some experiments conclude quickly with clear results, while others require extensive iteration, additional equipment, and consultation with external experts before reaching meaningful conclusions. Unlike traditional neural network inference where computational costs scaled predictably with input size, agent-based systems introduce variable reasoning depth, dynamic tool usage, and self-directed exploration that can cause identical queries to consume vastly different computational resources. Think of a symphony conductor who must balance multiple orchestras simultaneously, where each ensemble performs different pieces at different tempos, requiring constant coordination and resource reallocation based on the complexity of each composition. Multi-agent systems introduce similar coordination overhead, where multiple AI agents collaborate on complex tasks, sharing information, delegating subtasks, and synthesizing results in ways that create new patterns of resource consumption. Imagine a bustling town where residents don't follow predetermined schedules, but instead make decisions based on their interactions with neighbors, creating emergent patterns of activity that are impossible to predict from individual behavior alone. Agent-based AI systems exhibit similar characteristics, where multiple autonomous components interact dynamically, creating computational workloads that emerge from the interaction patterns rather than being directly programmed or easily forecastable. Consider an explorer who begins with a simple map, but must constantly adapt their route based on terrain discoveries, weather changes, and new opportunities, sometimes requiring completely different equipment and supplies than originally planned. Agentic AI systems operate with similar adaptability, where the computational path through a problem space depends on intermediate results, external tool responses, and dynamic decision-making that makes resource requirements inherently unpredictable. The infrastructure implications mirror the difference between operating a traditional factory with predictable production schedules versus managing an innovation lab where research teams might need vastly different equipment, time, and collaboration patterns depending on which scientific problems they're investigating on any given day. This variability in computational demand requires new approaches to capacity planning, resource allocation, and cost modeling. Think of a master gardener who has transitioned from growing uniform crops in neat rows to cultivating a complex ecosystem where different plants interact, support each other, and require varying amounts of attention throughout their interconnected growth cycles. Modern AI inference involves similar ecological complexity, where multiple reasoning processes, tool interactions, and feedback loops create computational ecosystems that resist simple optimization strategies. Memory usage patterns in agentic systems resemble a dynamic library where books are constantly being checked out, cross-referenced, and temporarily gathered into research clusters before being reorganized for the next inquiry,
rather than following the predictable access patterns of traditional inference workloads. Agents maintain context across multiple reasoning steps, accumulate tool outputs, and build complex state representations that grow and evolve throughout their problem-solving process.
The challenge becomes like managing a hospital emergency room, where you must maintain sufficient capacity for routine cases, while being prepared for complex trauma situations that might require coordinating multiple specialists, extended treatment times, and intensive resource utilization that's impossible to schedule in advance. Agentic inference demands infrastructure that can handle both simple queries and complex reasoning workflows efficiently. Power consumption follows similarly unpredictable patterns, like an art studio where some projects require only basic tools and brief sessions, while others demand specialized equipment running continuously for extended periods, making it difficult to predict electrical usage based solely on the number of artists working. Agent reasoning intensity, tool usage frequency, and iteration depth all contribute to variable energy consumption per query. Network bandwidth requirements fluctuate like a busy port, where some ships carry standard containers with predictable loading procedures, while others transport specialized cargo requiring custom handling, multiple cranes, and extended dock time, creating irregular patterns of resource utilization that resist traditional capacity planning approaches. Agent tool calls, external API interactions, and data retrieval patterns create similar network traffic variability. This variability creates new economic models similar to how premium consulting services price expertise and problem-solving capability rather than simple time units, because the value and cost of agentic AI depends more on the complexity of reasoning required than on predictable computational metrics. Organizations must balance the cost uncertainty of variable inference against the value of autonomous problem-solving capabilities. Cost optimization strategies shift from maximizing hardware utilization to optimizing for outcome quality and reasoning efficiency, like how a master craftsperson focuses on creating exceptional pieces rather than simply keeping their tools busy, because agentic systems derive value from their ability to solve complex problems autonomously, rather than from processing volume alone. The emergence of reasoning-intensive workloads creates natural differentiation between providers, similar to how medical practices specialize in routine care versus complex surgical procedures, because serving agentic AI workloads requires different infrastructure capabilities, expertise, and cost structures than traditional inference services, making it difficult for general-purpose providers to compete across all use cases. Quality metrics become more important than pure speed, resembling how fine dining restaurants measure success through customer satisfaction and culinary excellence, rather than simply maximizing table turnover, because agentic systems must balance reasoning thoroughness, accuracy, and resource efficiency in ways that resist simple performance optimization strategies. These economic complexities drive consolidation toward providers who can manage the operational sophistication required for agentic workloads, like how complex legal cases gravitate towards specialized law firms with the resources, expertise, and infrastructure needed to handle multi-year litigation processes that smaller practices cannot efficiently support. Understanding these new economic patterns becomes essential for making informed decisions about when to deploy agentic AI, how to structure pricing models, and whether to build internal capabilities or partner with specialized providers, much like how businesses choose between hiring full-time specialists versus consulting with experts on a project basis, depending on their specific needs and resource constraints.
What we just explored together was how AI agents work more like detectives, coordinating multiple specialists, rather than simple systems with predictable costs. These agentic systems introduce uncertainty, because each request might trigger complex reasoning processes that vary dramatically in their computational needs. Let that complexity settle softly in your mind. You don't need to solve it, just acknowledge it. As we continue our peaceful journey through these ideas, we'll see how this uncertainty plays out in real-world applications. A next section will show us how financial institutions are grappling with these new realities when they deploy AI for trading decisions.
Large language models are transforming how financial institutions make trading decisions. Much like a master librarian who can instantly read through thousands of books and pull out exactly the insights you need. These AI systems digest financial news, social media sentiment, earnings reports, and market data to predict stock movements and automate investment strategies with remarkable precision, processing vast amounts of unstructured information that would take human analysts weeks to review.
The Strategic Technology Analysis Center has spent over 15 years developing benchmarks for financial workloads, and their latest creation, STAC AI, focuses specifically on testing the complete retrieval augmented generation and LLM inference pipeline that modern trading systems depend on. Think of STAC AI as a standardized obstacle course designed specifically for financial AI systems, where each challenge mirrors real-world tasks that trading algorithms encounter daily, ensuring that performance measurements reflect actual deployment conditions rather than artificial scenarios.
The STAC AI Lang 6 benchmark zeroes in on LLM inference performance using two different llama models, the 8B and 70B parameter versions, each tested against carefully crafted financial datasets. Like a chef preparing two different sized meals for varying appetites, the benchmark uses Edgar-4 for medium-length requests that summarize company relationships to commodities and currencies, while Edgar-5 tackles long context requests covering complete 10K filings, testing how well systems handle both quick summaries and comprehensive document analysis. These datasets draw from real Edgar filings, those dense annual reports that publicly traded companies must submit, covering thousands of companies over 5 years of financial data. Picture a vast archaeological dig where each layer represents a different year of corporate history, and the AI systems must excavate specific insights about how companies relate to various financial instruments, real estate sectors, and market conditions, transforming regulatory paperwork into actionable trading intelligence. The benchmark tests two distinct operational modes that mirror how trading systems actually work in practice, like a factory that can either process large batches during quiet periods or handle individual orders as they arrive throughout the trading day. Batch mode delivers all requests simultaneously and measures pure throughput, while interactive mode simulates real-time trading conditions where requests arrive at pseudo-random intervals, measuring reaction time, words per second, and output rate per user to capture the delicate balance between speed and responsiveness. Interactive mode introduces a crucial parameter called the mean arrival rate, lambda, which controls how frequently new requests hit the system, much like adjusting the flow rate on a garden sprinkler to match different watering needs. The benchmark captures reaction time, analogous to time to first token in other testing frameworks, and tracks the output rate per user, allowing engineers to understand how system performance degrades or maintains quality as the request load increases throughout busy trading periods. An important distinguishing feature of STAC AI requires that chat templates and tokenization happen during inference rather than being pre-processed, like a translator who must parse and understand each incoming message in real time rather than working from pre-translated scripts. This reflects real deployment scenarios where financial institutions prefer server-side processing to protect their proprietary system prompts, even though this approach places additional computational load on the CPU components of the inference pipeline. NVIDIA's recent benchmark results showcase 3 distinct hardware configurations, each representing different deployment strategies that financial institutions might choose based on their specific needs and constraints.
The HPE ProLiant DL384 Gen 12, powered by NVIDIA GH200 Grace Hopper Superchip, provides an efficient single-server solution, like a compact but powerful workshop that combines multiple specialized tools in one integrated workspace, offering both CPU and GPU capabilities in a unified architecture designed for space-conscious data centers. The cloud-based Lambda instance features 8 NVIDIA Blackwell B200 GPUs in an HGX platform, connected through high-speed NVLink and NVSwitch technology, resembling a high-performance orchestra where each musician can communicate instantly with every other performer. Each B200 GPU brings 180 gigabytes of HBM3E memory and 8 terabytes per second of memory bandwidth, providing the substantial memory resources needed for large model inference while maintaining the tight coordination required for distributed processing across multiple accelerators. The Supermicro configuration pairs 2 NVIDIA RTX Pro 6000 Blackwell Server Edition GPUs, each equipped with 96 gigabytes of memory, creating a system that functions like a well-balanced tandem bicycle where both riders contribute substantial power while maintaining perfect synchronization. This setup demonstrates how organizations can achieve impressive performance for AI development and deployment within a smaller system footprint, providing aggregate GPU memory sufficient for larger models, bigger batch sizes, or multiple concurrent inference jobs. The quantization strategy varies by hardware platform, much like a photographer choosing different film types to match specific lighting conditions and desired image characteristics. NVIDIA Hopper systems use FP8 quantization, while Blackwell platforms leverage the newer NVFP4 format, with all quantization performed using NVIDIA TensorRT Model Optimizer to ensure that each deployment achieves optimal performance with the most efficient computational kernels available for that particular hardware architecture. TensorRT LLM serves as the inference framework across all tested configurations, functioning like a sophisticated transmission system that efficiently transfers power from the engine to the wheels, while adapting to different driving conditions. The framework provides a PyTorch runtime that offers familiar development experience while maintaining peak performance, allowing engineers to work with tools they know while accessing the full computational capabilities of the underlying hardware accelerators. In batch mode testing, NVIDIA Blackwell delivered substantial performance improvements across all scenarios, with the HGX B200 system achieving 52,823 words per second and 311 requests per second on Llama 3.1 8B with the Edgar-4 dataset. These results unfold like a river system where the main channel carries dramatically more water than its tributaries, with Blackwell's performance representing the powerful main flow compared to the smaller streams of previous generation hardware, demonstrating clear generational improvements in processing capability. The performance scaling becomes even more pronounced with larger models and longer contexts, where the HGX B200 achieved 12,040 words per second for Llama 3.1 70B on Edgar-4, compared to 1,071 words per second on the GH200 system. This represents nearly an order of magnitude improvement, like upgrading from a small delivery truck to a massive freight train, where the increased capacity enables handling substantially larger workloads while maintaining efficient operation across the expanded scale of operations. Interactive mode results reveal the critical balance between throughput and user experience, measured through reaction time and interword latency, much like a skilled waiter managing multiple tables who must balance speed of service with attention to each individual customer. The benchmark plots these metrics across different arrival rates, creating a Pareto frontier that shows how systems trade off raw processing power against responsiveness, helping engineers understand the practical limits of their deployment configurations.
The HGX B200 system consistently achieved superior performance across this interactivity throughput trade-off space, maintaining lower reaction times and interword latencies even at higher throughput levels, like a master juggler who can handle more objects while keeping each one in the air longer than less skilled performers. This demonstrates that Blackwell architecture doesn't just provide raw speed improvements, but also maintains better quality of service characteristics under varying load conditions. For organizations wanting to benchmark their own systems, NVIDIA provides a comprehensive tutorial that walks through the entire process, starting with model quantization and dataset preparation, much like a detailed recipe that guides cooks through each step of preparing a complex dish. The process begins with launching a Docker container that includes all necessary dependencies, followed by cloning the TensorRT Model Optimizer repository and executing quantization scripts tailored to specific model requirements and hardware capabilities. The quantization process transforms models like Llama 3.1 8B Instruct into optimized formats such as NVFP4, reducing memory requirements and improving inference speed while maintaining accuracy, similar to how a skilled craftsman compresses a complex mechanism into a more efficient form without losing functionality. This optimization step proves crucial for achieving the performance levels demonstrated in the Stack AI benchmark results, enabling larger models to fit in available memory while processing requests more rapidly. Dataset generation uses synthetic data that matches the token distribution characteristics of real workloads, functioning like a simulator that creates realistic training conditions without requiring access to proprietary financial data. The benchmark utility can generate thousands of requests with specified input and output sequence links, allowing organizations to test their systems against workloads that closely approximate their actual deployment scenarios, while maintaining data privacy and security requirements. The final benchmarking step executes these synthetic requests through TensorRT LLM runtime in offline mode, sending all requests simultaneously to measure pure throughput performance, much like a stress test that pushes a bridge to its maximum load capacity to understand its operational limits. The system outputs comprehensive metrics, including request throughput, tokens per second per GPU, and various latency measurements, providing the detailed performance profile needed for capacity planning and system optimization decisions. These benchmark results establish NVIDIA Blackwell as a significant advancement for financial AI applications, delivering up to 2.8 times the performance of previous architectures while maintaining superior interactive responsiveness. Like a new generation of race car that not only achieves higher top speeds, but also handles corners more smoothly and responds more precisely to driver input. The RTX Pro 6000 results demonstrate platform flexibility, showing competitive performance even in smaller 2 GPU configurations running on Red Hat OpenShift, proving that organizations can right-size their deployments from cost-efficient servers to full data center nodes while maintaining Blackwell's performance advantages.
We've just seen how large language models are transforming financial trading, processing vast amounts of information like a master librarian, and how researchers have created specialized benchmarks to test these systems under real-world conditions. The technical details of Stack AI benchmarks might feel intricate, but the heart of it is simple. People are working hard to understand and measure these new capabilities. Let these thoughts settle gently as we turn to something quite beautiful in the world of AI research. Our next exploration will show us how AI systems are learning to improve themselves through reflection, much like keeping a thoughtful journal. Tonight, we're settling into a particularly elegant piece of research that addresses one of the most persistent challenges in artificial intelligence: the question of how language models can learn from their mistakes without the computational burden of traditional training methods. Like a gardener who learns to tend their plants better, not by replacing their entire knowledge,
but by keeping a detailed journal of what worked and what didn't. Researchers have developed a framework called reflection that allows language agents to improve through verbal self-reflection rather than expensive model retraining. The core insight here is beautifully simple, that instead of updating the neural network weights through countless training examples, these agents can literally talk themselves through their experiences, building up a memory of lessons learned that guides future decision-making. This approach sidesteps the traditional reinforcement learning bottleneck, where agents need massive amounts of trial and error data and computationally expensive fine-tuning to show meaningful improvement.
The reflection framework operates through a process that mirrors how thoughtful humans approach complex problems,
where agents engage in verbal reflection about the feedback they receive from their environment. Think of it like a chess player who, after each game, sits quietly and walks through their moves, articulating what they learned about their opponent's strategy, their own tactical errors, and what they might do differently next time. These language agents interact with external environments, whether those are programming compilers that give error messages, game environments that provide success or failure signals, or API systems that return specific responses, and then they process this feedback through structured self-reflection. Rather than simply moving on to the next task, the agents pause to verbally analyze what happened, why certain actions led to particular outcomes, and how they might adjust their approach going forward, creating rich, linguistic representations of their learning experience.
The episodic memory buffer serves as the cornerstone of this approach,
functioning as a repository where agents store their reflective insights for future reference. Picture a ship's logbook, where the captain records not just the basic facts of each voyage, the weather conditions, the course taken, the ports visited, but also the nuanced observations about what navigation decisions worked well in particular situations, and what might be adjusted for similar future circumstances. This memory system allows reflection agents to accumulate wisdom across multiple interactions, building up a personalized knowledge base that goes beyond their initial training and captures the specific lessons learned from their own trial and error experiences. The beauty of this episodic memory is that it creates a form of meta-learning, where agents don't just solve individual problems, but develop increasingly sophisticated strategies for approaching entire classes of problems based on their accumulated reflective observations.
One of the most remarkable aspects of reflection
is its flexibility in handling different types of feedback signals, accommodating everything from simple scalar rewards to complex free-form language descriptions. Like a skilled translator who can work equally well with formal diplomatic documents, casual conversation, poetry, or technical manuals, adapting their approach to the specific nuances and requirements of each text type, reflection agents can process and learn from whatever kind of feedback their environment provides. Whether the feedback comes from external sources, such as a coding compiler returning specific error messages, or from internally simulated evaluation processes, where the agent assesses its own performance, the framework can incorporate these diverse signals into its reflective process. This adaptability makes reflection particularly powerful because it doesn't require environments to be specially designed or feedback to be formatted in specific ways, instead working with the natural feedback that emerges from real-world interactions.
The experimental results demonstrate the practical power of this approach, with reflection achieving a remarkable 91% pass rate on the human eval coding benchmark, substantially outperforming the previous state-of-the-art GPT-4 result of 80%. Like a student who, through careful review of their mistakes and thoughtful analysis of their problem-solving process, manages to surpass even naturally gifted peers who rely solely on raw ability. These reflection agents show that systematic self-reflection can lead to performance improvements that go beyond what the underlying language model could achieve through its initial training alone. The framework proved effective across diverse task domains, from sequential decision-making challenges that require planning over multiple steps, to coding problems that demand precise logical reasoning, to language reasoning tasks
that involve complex inference and analysis. This broad applicability suggests that verbal self-reflection taps into something fundamental about how intelligent systems can bootstrap their own learning. The research also includes careful ablation studies that examine how different components of the system contribute to its overall effectiveness, exploring variations in feedback signal types, methods for incorporating reflection into decision-making, and different agent architectures. Think of this like a master chef systematically testing their signature recipe, trying the dish with different combinations of spices, cooking techniques, and ingredient proportions to understand exactly which elements are essential and which can be modified while maintaining the overall excellence of the result. These studies provide valuable insights into the mechanisms behind reflection's success, helping researchers understand not just that the approach works, but why it works and how it might be further refined or adapted to new domains. The systematic analysis reveals the delicate interplay between reflection quality, memory organization, and feedback processing that enables agents to transform their mistakes into stepping stones toward better performance. As we drift toward sleep, it's worth reflecting on how this work represents a shift toward more human-like learning in artificial intelligence, where improvement comes not through brute force computation, but through thoughtful analysis and self-awareness. Like a wise mentor who guides students not by providing more information, but by helping them think more clearly about what they already know and have experienced. Reflection shows us that sometimes the path to better AI performance lies not in bigger models or more data, but in more sophisticated ways of processing and learning from experience. This research opens up intriguing possibilities for creating AI systems that can adapt and improve in real time, building up their own expertise through interaction with the world, much as humans do throughout their lives, carrying forward the lessons learned from each challenge to inform their approach to the next.
We've just discovered the elegant concept of reflection, where AI agents improve by talking themselves through their experiences, rather than requiring expensive retraining, like a gardener keeping a detailed journal of lessons learned. There's something deeply satisfying about this approach, isn't there? It mirrors how we humans learn from our mistakes through reflection. Take a quiet moment to appreciate this insight. As we move forward in our gentle exploration, we'll encounter an even more ambitious vision, an AI agent that learns endlessly in a virtual world, building skills and making discoveries entirely on its own.
In the vast digital landscapes of research laboratories around the world, scientists have been working toward a particular dream, one that involves creating artificial agents capable of learning and exploring on their own, much like a curious child discovering the world around them. But this child never tires, never forgets, and continuously builds upon everything it learns. A new breakthrough called Voyager represents the first of its kind, an embodied agent powered by large language models that lives and learns within the virtual world of Minecraft, exploring endlessly, acquiring new skills, and making discoveries without any human guidance or intervention, marking a significant milestone in the field of autonomous artificial intelligence. The architecture of Voyager resembles a well-orchestrated symphony, with three distinct but harmoniously working components that enable its remarkable capabilities. The first component serves as an automatic curriculum, designed specifically to maximize exploration by continuously setting new goals and challenges for the agent, ensuring it never becomes complacent or stuck in repetitive behaviors, but instead pushes the boundaries of what it can discover and accomplish in its virtual environment. The second cornerstone of Voyager's design functions like a vast, meticulously organized library. But instead of books, this repository stores executable code that represents complex behaviors and skills the agent has learned throughout its journey. This ever-growing skill library serves as both a memory bank and a toolkit, allowing Voyager to retrieve and reuse sophisticated behaviors it has mastered, while also providing a foundation upon which to build even more complex capabilities, creating a compounding effect that accelerates learning over time. Perhaps, most ingeniously, Voyager employs a novel iterative prompting mechanism that works like a master craftsman refining a piece of work, continuously incorporating feedback from the environment, learning from execution errors, and performing self-verification to improve its programs and behaviors. This sophisticated feedback loop allows the agent to not merely execute pre-programmed actions, but to adapt, refine, and perfect its approaches based on real-time experience and outcomes, creating a truly dynamic learning system that evolves with each interaction. The technical implementation of Voyager leverages the power of GPT-4 for what researchers call black box queries, approach that functions like having a conversation with an expert consultant without needing to understand the intricate details of their thought processes. This design choice bypasses the typically complex and resource-intensive process of fine-tuning model parameters, making the system more accessible and practical to implement, while still harnessing the sophisticated reasoning capabilities of state-of-the-art language models. The skills that emerge from Voyager's learning process possess three particularly valuable characteristics that distinguish them from simpler automated behaviors, much like how a master chef's techniques are temporally extended across multiple steps, interpretable in their logic and purpose, and compositional in how they can be combined to create entirely new culinary experiences. These properties enable Voyager's abilities to compound rapidly as new skills build upon existing ones, while also providing protection against catastrophic forgetting, the common problem where artificial agents lose previously learned capabilities when acquiring new ones. When researchers put Voyager to the test in empirical evaluations, the results painted a picture of exceptional performance that resembled a thoroughbred racehorse, outpacing its competitors by remarkable margins. The agent demonstrated the ability to obtain 3.3 times more unique items than previous state-of-the-art approaches, traveled 2.3 times longer distances in its explorations, and perhaps most impressively, unlocked key technological milestones in Minecraft's progression system up to 15.3 times faster than competing methods, showcasing its superior learning efficiency and exploratory capabilities. Beyond raw performance metrics, Voyager exhibited something even more valuable in the realm of artificial intelligence, a quality that functions like a seasoned traveler's ability to adapt their skills and knowledge to navigate completely new destinations with confidence and competence. When placed in entirely new Minecraft worlds, Voyager could effectively utilize its previously learned skill library to tackle novel tasks from scratch, demonstrating true generalization capabilities, while other techniques struggled to transfer their learning to these unfamiliar environments, often failing to adapt or perform effectively. The implications of Voyager's success extend far beyond the virtual blocks and landscapes of Minecraft, much like how the Wright brothers' first flight at Kitty Hawk represented not just a brief moment in the air, but the dawn of an entirely new era of human capability and exploration. This work represents a significant step toward truly autonomous AI agents that can continuously learn, explore, and adapt in complex environments without human oversight, opening pathways for applications in robotics, autonomous systems, scientific discovery, and countless other domains where persistent, adaptive learning is valuable. The research team's decision to open source their complete codebase and prompts reflects the collaborative spirit of scientific advancement, functioning like a master gardener sharing not just the beautiful flowers they've cultivated, but also the seeds, techniques, and knowledge needed for others to grow their own magnificent gardens. This transparency enables other researchers to build upon Voyager's foundations, potentially accelerating progress in embodied AI and lifelong learning, while also allowing the broader scientific community to validate, extend, and improve upon these groundbreaking techniques in the ongoing quest to create truly intelligent, autonomous agents.
someone else is awake right now, listening to this very moment with you.
If that's you, leave a word below, so the rest of us know we're not alone at this hour. We just met Voyager, that remarkable AI agent living and learning autonomously in the world of Minecraft, exploring endlessly like a curious child who never tires and never forgets. The image of this digital explorer, continuously building upon everything it learns, might feel both wonderful and perhaps a little overwhelming. That's perfectly natural. Let yourself rest with the wonder of it. As we continue our quiet journey together, we'll explore how AI systems are learning to combine thinking with acting, weaving reasoning and action together, like a chef who can taste and adjust while cooking.
Like a chef who can both taste and adjust seasoning while cooking, rather than following a rigid recipe. Large language models have typically been trained to either reason through problems step by step or take actions in response to situations, but rarely to do both simultaneously in a coordinated dance. The REACT approach represents a fundamental shift in how we think about AI problem solving, allowing language models to weave together chains of reasoning with concrete actions in an interleaved pattern, where each type of thinking enhances and informs the other. This synergy creates a more robust and flexible system, one that can pause to think, act on that thinking, observe the results, and then reason again based on what it learned, much like how humans naturally approach complex problems in the real world.
Think of this integration as resembling a detective working a case, where the reasoning traces serve as the investigator's internal monologue, helping to induce new theories, track evolving leads, update plans as evidence emerges, and handle unexpected complications that arise during the investigation. These reasoning components don't exist in isolation, though, because they're paired with actions that allow the model to interface with external sources, gathering fresh information from knowledge bases, environments, or other systems that can provide the missing pieces of the puzzle. The beauty of this approach lies in how the reasoning and acting components feed into each other, creating a continuous loop of thinking, doing, observing, and adapting that makes the overall system far more capable than either component would be on its own. The researchers put their REACT method to the test across a diverse landscape of language understanding and decision-making tasks, demonstrating its effectiveness against state-of-the-art baseline methods, while also showing improved human interpretability and trustworthiness compared to approaches that lack either reasoning or acting components. Like a Swiss Army knife that proves its versatility across different practical situations, REACT showed consistent improvements across multiple domains, suggesting that this interleaved approach to reasoning and acting represents a genuinely robust advancement rather than a narrow optimization for specific types of problems. The method's ability to outperform existing techniques while remaining interpretable to human observers addresses two critical challenges in AI development: the dual needs for performance and explainability. On question-answering tasks, using Hotpot QA and fact verification challenges from the Fever dataset, REACT demonstrated a particularly elegant solution to some of the most persistent problems plaguing chain-of-thought reasoning approaches, namely hallucination and error propagation. Picture a librarian who can both think through where information might be located and actually walk to the shelves to verify their hunches, rather than trying to remember everything from memory and potentially making mistakes that compound over time. By interacting with a simple Wikipedia API, the REACT system could ground its reasoning in actual factual information, checking and double-checking its assumptions, rather than building elaborate chains of reasoning on potentially faulty foundations, which dramatically reduced both the tendency to generate false information and the cascade of errors that often follows initial mistakes. The trajectories that REACT generated during these question-answering and fact verification tasks showed a remarkably human-like quality in their task-solving approaches, creating step-by-step paths that human evaluators found significantly more interpretable than the outputs of baseline methods without reasoning traces.
like reading the thought process of a student showing their work on a complex math problem. These trajectories revealed not just the final answer, but the logical progression of thoughts and actions that led to that conclusion, making it much easier for humans to understand, verify, and trust the system's decision-making process. This interpretability represents a crucial advancement in AI transparency, allowing users to follow along with the model's reasoning and catch potential errors before they lead to problematic outcomes. When tested on interactive decision-making benchmarks, specifically AlphaWorld and WebShop, React achieved even more dramatic performance improvements, outperforming both imitation learning and reinforcement learning methods by substantial margins, with absolute success rate improvements of 34% on AlphaWorld and 10% on WebShop. Perhaps most remarkably, like a master craftsperson who can demonstrate expertise with just a few examples, rather than requiring extensive training, the React approach achieved these superior results while being prompted with only one or two in-context examples, rather than needing the extensive training datasets typically required by imitation and reinforcement learning approaches. This efficiency in learning from limited examples suggests that the reasoning-acting synergy taps into something fundamental about how intelligent problem-solving actually works, leveraging the model's existing language understanding capabilities more effectively than previous approaches. The implications of this research extend far beyond the specific tasks tested, pointing toward a more general principle about how we might design AI systems that need to operate effectively in complex, dynamic environments where both careful thinking and decisive action are required. Like a bridge that connects two previously separate islands, React demonstrates how reasoning and acting capabilities can be integrated to create something more powerful than the sum of its parts, opening up new possibilities for AI applications that require both deep understanding and real-world interaction. The fact that this integration improves performance while also enhancing interpretability suggests that we're moving toward AI systems that are not only more capable, but also more trustworthy and easier for humans to work with. A combination that will be essential as these technologies become more widely deployed in critical applications.
We've just explored the React approach, where AI systems learn to weave together chains of reasoning with concrete actions, like a detective working a case who can think, investigate, observe, and reason again based on new evidence. This coordination between thinking and doing represents something quite sophisticated in AI development. Take a gentle breath and let this idea settle. As we move deeper into our evening together, we'll step back to see the bigger picture of how researchers are mapping this entire emerging landscape of AI agents built on large language models. Tonight, we'll explore a comprehensive survey that maps the emerging landscape of artificial intelligence agents built upon large language models, a field that represents one of the most promising pathways toward creating AI systems that can think, perceive, and act in our complex world. Like a master architect surveying the foundation stones before designing a grand cathedral, researchers have long sought the right building blocks for artificial general intelligence. And this paper argues that large language models may finally provide that essential foundation. The authors trace how the ancient philosophical dream of artificial beings has evolved through decades of AI research, where previous efforts focused on enhancing specific capabilities or optimizing performance on narrow tasks, but lacked a general, powerful starting point for creating truly adaptable agents. Now, with the remarkable versatility demonstrated by large language models, researchers see genuine hope for building AI agents that can navigate diverse scenarios with human-like flexibility and understanding. The survey introduces an elegant three-component framework that captures how these LLM-based agents operate, much like how a skilled conductor orchestrates a symphony through three essential elements: the musical score, the musician's interpretation, and the resulting performance. The framework consists of what the authors call the brain,
perception, and action components, where the brain represents the core LLM that processes information and makes decisions. Perception encompasses how the agent senses and interprets its environment, and action covers how it executes decisions and interacts with the world around it. This framework proves remarkably adaptable, allowing researchers to customize and configure agents for vastly different applications, from simple task automation to complex reasoning challenges. The beauty of this structure lies in its modularity, where each component can be refined and enhanced while maintaining the overall coherence of the agent's behavior.
The researchers examine how these LLM-based agents operate across 3 distinct but interconnected domains, each revealing different aspects of their potential and complexity. In single-agent scenarios, individual agents work independently to solve problems, make decisions, and complete tasks, demonstrating their capacity for autonomous reasoning and action, like a skilled craftsperson working alone in their workshop, applying years of knowledge and technique to create something meaningful. The authors then explore multi-agent scenarios where multiple AI agents collaborate, compete, or coordinate their efforts, revealing emergent behaviors and collective intelligence that neither agent could achieve alone. Finally, they investigate human-agent cooperation, examining how these AI systems can work alongside humans as partners, assistants, or collaborators, enhancing human capabilities rather than simply replacing them. Perhaps most fascinatingly, the survey delves into the concept of agent societies, where collections of LLM-based agents develop their own social dynamics, personalities, and behavioral patterns that mirror and illuminate aspects of human social organization. Like watching a bustling marketplace emerge from individual vendors, customers, and interactions, researchers observe how agent societies spontaneously generate complex social phenomena, hierarchies, and communication patterns that weren't explicitly programmed into any individual agent. The authors explore how these artificial beings develop distinct personalities and behavioral quirks, how they form relationships and alliances, and how their collective behavior creates insights into the fundamental principles that govern social interaction. These agent societies serve as both testing grounds for AI development and unexpected mirrors that reflect back new understanding about human social behavior, group dynamics, and the emergence of culture and cooperation. The paper acknowledges that this exciting field still faces significant challenges and open questions that will shape its future development, much like early cartographers marking unknown territories on their maps with careful notation of what remains to be explored. The authors discuss key limitations in current LLM-based agents, including issues with consistency, reliability, and the ability to handle truly novel situations that fall outside their training data. They examine questions about how to ensure these agents behave ethically and safely, particularly as they become more autonomous and capable of taking actions with real-world consequences. The survey also addresses technical challenges around computational efficiency, memory management, and the integration of different types of knowledge and reasoning capabilities. Throughout their comprehensive analysis, the researchers maintain that LLM-based agents represent a fundamental shift in AI development, moving away from narrow, task-specific systems toward more general, adaptable artificial intelligence that can learn, reason, and act across diverse domains. Like a Swiss Army knife that replaces a toolbox full of single-purpose instruments, these agents offer the versatility and general capability that the AI community has long sought as a foundation for building truly intelligent systems. The survey serves not just as a review of current progress, but as a roadmap for future research, highlighting the most promising directions and the most pressing challenges that need to be addressed. The author's work provides both newcomers and experts with a clear understanding of where the field stands and where it might be headed. As we settle into sleep, consider how this survey captures a pivotal moment in artificial intelligence history, where the convergence of powerful language models and agent-based AI architectures opens new possibilities for creating artificial beings that can truly understand, reason, and act in our world. The paper's systematic exploration of LLM-based agents,
from individual capabilities to complex societies, offers a glimpse into a future where artificial intelligence might finally achieve the general, adaptable intelligence that has been the field's holy grail for decades. Like seeds planted in fertile soil, these early LLM-based agents may grow into something far more remarkable than we can currently imagine, and this comprehensive survey helps us understand both the promise and the responsibility that comes with nurturing such powerful technology. Rest well, knowing that researchers are carefully mapping this new frontier, balancing ambition with wisdom as they work toward AI systems that can genuinely benefit humanity.
What we just encountered was a comprehensive survey mapping the emerging landscape of AI agents, tracing how the ancient dream of artificial beings has evolved to this moment, where large language models might finally provide the foundation for truly adaptable intelligence. It's a grand vision, like an architect surveying foundation stones before designing a cathedral. Rest with that sense of historical significance for a moment. Our next gentle exploration will show us how multiple AI agents are learning to work together, like musicians in an orchestra, creating something more beautiful than any solo performance.
In the quiet landscape of artificial intelligence research, there's been a fascinating shift toward letting multiple AI agents work together, much like a well-coordinated orchestra, where each musician contributes their unique voice to create something more beautiful than any solo performance could achieve. The researchers behind AutoGen have created what they describe as an open-source framework, a kind of foundational toolkit that allows developers to build applications where multiple large language models can converse with each other, exchanging ideas and information to accomplish complex tasks that might overwhelm a single AI system working in isolation. What makes AutoGen particularly elegant is how customizable these digital agents can be, like having a collection of specialized craftsmen in a workshop, each with their own tools, skills, and ways of approaching problems. The framework doesn't lock developers into rigid structures, but instead offers flexibility in how these agents are designed and deployed, allowing them to operate in various modes that can seamlessly blend the capabilities of large language models with human input when needed, and with external tools that extend their reach into the real world beyond pure text generation.
The conversational nature of these agents creates something quite remarkable, resembling the way ideas bounce back and forth in a good dinner party conversation, where each participant builds on what others have said, asks clarifying questions, and contributes their own insights to gradually develop a richer understanding of the topic at hand. This multi-agent approach allows for a more natural problem-solving process, where different AI systems can specialize in different aspects of a challenge, debate approaches, check each other's work, and arrive at solutions through collaborative reasoning rather than the sometimes limited perspective of a single model. One of the most intriguing aspects of AutoGen is how developers can define agent interaction behaviors with remarkable flexibility, like a director choreographing a dance, where the performers can improvise within a structured framework. The system accepts both natural language instructions and computer code as ways to program these conversation patterns, which means that creating sophisticated multi-agent applications doesn't require developers to learn entirely new programming paradigms, but can build on familiar approaches while opening up new possibilities for agent coordination and task distribution.
The framework serves as what the researchers call a generic infrastructure, functioning like the electrical grid that powers a city, providing the underlying systems and standards that allow a diverse array of applications to be built on top, without each developer having to reinvent the fundamental mechanisms of agent communication and coordination. This infrastructure approach means that AutoGen can support applications of varying complexity levels and can adapt to work with different types and capacities of large language models, making it accessible to projects with different computational resources and requirements.
The empirical studies conducted by the research team paint a picture of remarkable versatility, like a Swiss Army knife that proves useful across an unexpectedly wide range of situations and challenges. Their testing spanned domains from mathematics and coding, where logical precision is paramount, to question answering and operations research, where different types of analytical thinking come into play, and even extending into online decision-making and entertainment applications, demonstrating that the multi-agent conversation approach has broad applicability across both serious technical domains and more creative, exploratory use cases. What emerges from this research is a compelling vision of how large language models might evolve beyond the current paradigm of single-agent interactions, moving toward more sophisticated collaborative systems that mirror how humans often work best together, like members of a research team where different experts contribute their specialized knowledge to tackle multifaceted problems. The effectiveness demonstrated across such diverse application domains suggests that multi-agent conversation isn't just a novel technical approach, but potentially a fundamental advancement in how we think about deploying artificial intelligence for complex, real-world tasks. The open-source nature of AutoGen carries particular significance in the current AI landscape, functioning like a public library that makes powerful resources available to a broad community of developers and researchers rather than keeping them locked away in proprietary systems. This accessibility means that the multi-agent conversation approach can be explored, refined, and extended by developers working on everything from academic research projects to commercial applications, potentially accelerating the development of new use cases and improvements to the underlying framework. From a technical perspective, the ability to combine LLMs, human inputs, and external tools within a single conversational framework represents a significant step toward more practical AI applications, like having a translator who can seamlessly switch between languages as needed, rather than being limited to just one mode of communication. This hybrid approach acknowledges that different types of problems may require different types of intelligence and different types of tools, and that the most effective AI systems of the future may be those that can orchestrate these various capabilities, rather than trying to encompass everything within a single model. As we consider the broader implications of this research, AutoGen appears to offer a glimpse into a future where artificial intelligence becomes more collaborative and distributed, resembling an ecosystem where different species fill different niches and work together in complex relationships rather than competing in isolation. The framework's demonstrated effectiveness across domains, as varied as mathematics and entertainment, suggests that multi-agent conversation may become a standard approach for building sophisticated AI applications, moving us closer to systems that can handle the kind of complex, multifaceted challenges that characterize most real-world problems.
We've just learned about AutoGen and how it enables multiple AI agents to work together like a well-coordinated orchestra, each contributing their unique voice to accomplish complex tasks through conversation and collaboration. The idea of AI systems talking with each other to solve problems might feel both fascinating and strange. That's perfectly fine. Let these thoughts rest gently in your mind. As we approach the end of our journey together tonight, we'll explore one final, quite magical development: AI agents that live their own digital lives in ways that simulate believable human behavior.
Imagine, if you will, a digital terrarium where tiny glass figurines have somehow learned to live their own lives. And you'll begin to grasp what researchers have accomplished in creating what they call generative agents, computational software that simulates believable human behavior in ways that could transform how we build interactive applications, from immersive virtual environments to practice spaces for difficult conversations to tools for prototyping social systems. These aren't simple chatbots or scripted characters, but rather digital beings that wake up in the morning, prepare breakfast, head off to their work,
create art or write stories, form opinions about their world, notice one another, strike up conversations, remember their experiences, and plan for tomorrow based on what they've learned from yesterday.
The technical architecture underlying these agents works much like a sophisticated personal journal combined with a strategic planner, extending large language models with three crucial capabilities that mirror how humans navigate their daily lives. First, the agents maintain a complete record of their experiences using natural language, storing every interaction, observation, and event in a way that preserves the rich context of their digital existence. Second, they synthesize these accumulated memories over time into higher-level reflections, much as we might look back on a week of experiences and draw broader conclusions about relationships, preferences, or goals. Third, they dynamically retrieve relevant memories to inform their behavior planning, allowing past experiences to shape present decisions in contextually appropriate ways. To test this architecture, the researchers created what amounts to a digital ant farm populated with 25 generative agents, living in an interactive sandbox environment inspired by The Sims, where human users can observe and interact with this small town using natural language. The agents don't simply follow predetermined scripts, but rather develop their own routines, relationships, and responses to the evolving social dynamics of their community. This experimental setup provides a controlled, yet rich environment for studying how computational agents can exhibit both individual personality traits and emergent social behaviors that arise naturally from their interactions with one another. The true test of these agents' believability emerged in their handling of a social event that began with just a single seed, like watching ripples spread across a still pond after dropping in a pebble. When researchers specified that one agent wanted to throw a Valentine's Day party, they observed how this simple desire propagated through the agent community over the following 2 days. The agents autonomously began spreading invitations, introducing themselves to others they hadn't met before, asking each other out on dates specifically for the party, and coordinating their schedules to ensure they could attend together at the appropriate time, all without any additional programming or intervention from the researchers. Through careful ablation studies, the researchers demonstrated that each component of their agent architecture contributes critically to believable behavior. Much like removing individual instruments from an orchestra reveals how each contributes to the overall symphony. The observation component allows agents to perceive and encode their environment and social interactions. The planning component enables them to set goals and determine actions based on their current understanding. And the reflection component provides the metacognitive ability to learn from experience and update their worldview over time. When any of these components were removed or impaired, the agent's behavior became noticeably less realistic and engaging. This research represents a significant fusion of large language models with computational interactive agents, introducing new architectural and interaction patterns that could reshape how we approach behavioral simulation in computing, like discovering a new type of lens that brings previously blurry images into sharp focus. The implications extend far beyond entertainment applications, potentially enabling more sophisticated training simulations for healthcare professionals, educational environments where students can practice interpersonal skills with responsive virtual humans, or research tools for studying social dynamics and human behavior in controlled yet naturalistic settings. The work addresses a fundamental challenge in human-computer interaction, which is creating digital entities that feel genuinely alive and responsive, rather than mechanical or scripted, much like the difference between a player piano that can only repeat predetermined songs and a skilled musician who can improvise and respond to the mood of the room. By combining the linguistic sophistication of large language models with persistent memory, reflective reasoning, and dynamic planning capabilities, these generative agents cross an important threshold in believability that opens up new possibilities for how humans and artificial agents might collaborate
and coexist in digital spaces.
As we drift towards sleep, consider how this research illuminates the complex interplay between memory, reflection, and behavior that characterizes human social life, now captured in computational form, like preserving the essence of a garden in a detailed botanical illustration. These generative agents demonstrate that believable artificial behavior emerges not from simple rule following, but from the dynamic integration of experience, memory, and contextual reasoning, suggesting future applications where digital agents could serve as thoughtful collaborators, empathetic training partners, or insightful research subjects in our ongoing quest to understand and enhance human social interaction through technology.
And so we reach the end of our gentle exploration together, having traced this remarkable transformation from traditional AI economics to something entirely new. We've seen how the comfortable assumption of expensive training followed by cheap inference is giving way to a world where AI agents engage in unpredictable reasoning processes, creating that hidden explosion in costs that our title promised to reveal. We've walked through AI factories, sophisticated hardware, financial applications, self-improving systems, and digital beings living their own lives. Let all of these ideas rest softly in your mind now. You don't need to carry them all with you into sleep. What matters is that you've touched something important about how our technological world is quietly changing. Rest well, knowing that tomorrow will bring its own discoveries, and for now, you can simply let go.